Hey everyone, welcome back to Take You Forward. So we will be discussing DP19 today, and the problem is going to be 01 knapsack. And this problem is a very important problem for any interview that you might have now or in the future. This is going to be one of the most common asked problems if you are given a problem in dynamic programming. Really, some variation can be asked, and which we'll be doing in the upcoming videos. So 01 knapsack. Now you might see a lot of videos, but in none of the videos they will be doing the space optimized approach of big O of W, not even two rows. You're gonna optimize this into a single array. Yes, as of now till DP18, we have been learning how to optimize, how to space optimize using two rows generally. But over here, we will be seeing how to optimize this using just a single row, and that's what we are going to learn. So 01 knapsack. Without waiting, let's get started. What is the problem stating? The problem is stating there is a thief. Okay, there is a thief who goes to some house to steal items, and in that house there are three items, like there are n items, and let's assume there are three items. Each of the item has a particular weight and a particular value. So let's assume there are items with weight 3, 4, 5, and the weight 3 item will cost you will have a value 30, this will have a value 50, and this will have a value 60. So thief has gone, obviously he's gonna steal out things. So he cannot steal, like he cannot just take things in his hand and go. So what he has, he has a bag. Okay, and this bag, now a bag cannot carry everything in the home. It can only carry items till it does not exceeds the given weight, and over here the given weight is 8. The bag can carry as long as it does not exceeds the weight 80. Now if you're going to steal at a home, like if you're the thief and you're going to steal at a home, what is the first thing that you'll think? I'm going to steal in such a way that the value of those items should be maximized. So over here I'll be like, okay, fine, the thief will decide I'm going to steal this, and if I steal this, I'll have a value of 60, but my weight will reduce to 3 because this guy is having a weight of 5. So in my bag, 5 weight will be there. So I'll just be left out with the 3 weight. Next, he will be like, let's steal this. So we will steal this, and we will have another value of 30. This time, the value will reduce to 0. Now the thief cannot steal any further things because he has stolen this item, and his bag has got full. So he cannot steal this item. And in stealing both of these items, it manages to have a total value of 90. So the question states you will be given n, you'll be given a weight array, you'll be given a value array, right? And you'll be given a bag with a weight. You have to steal things from the home in such a way that this total value is as maximal as possible. Now you could have also gone with this guy and this guy. So if you'd have stolen the blue items, then the bag weight would have been 7, but the total value that you would have generated would have been 50 plus 30, which is 80. So thereby this is not a preferable way, because if you steal the blue items, then the total value is not maximum. The maximum that you can generate is 90. Why can't you steal this and this? Because the weight is 5 over here, the weight is 4 over here. So you cannot steal both the items because 5 plus 4 will be 9, and the bag permits you just 8 weight. Thereby this and this cannot be stolen together. Make sense? So you might be thinking, then Striver, we will apply greedy approach. We're like, Striver, the best thing is let's steal the valuable items at first, and then we will be stealing according to the weight left in our bag. Again, he's a thief, right? So he doesn't knows a lot of maths. So that's the first approach that you'll think. And I'll go to the house and I'll see, okay, this, let's assume this is an iPhone, this is the costliest thing, so I'll just put this into my bag. Similarly, I can assume that, okay, I'll take this mouse and put this into the bag because it is another costlier thing. thief will be going in the direction of picking up the most costlier thing. But if you go, will you do that? Let's analyze. Will the greedy approach work? The answer to that is no. Let's take an example. N is equal to 3, and let's take the bag that the thief is carrying is having a weight of, assume to be 6, okay? And I'm giving you weights and I'm giving you values. So assume there is a bag of weight, like there's an item of weight 5, there's an item of weight 3, there's an item of weight 2, okay? And this gives you 30 value, this gives you 40 value, and this gives you 60 value. Now since the weight of the bag is 6, since the weight of the bag is 6, if you go into the home, your first criteria will be I'll steal the costliest thing. And the costliest thing comes out to be this. Like I'll steal this one because it's the costliest. So I will have a value of 60, and the bag will just have a space of 1 remaining because I've stolen 5. Can you steal this now? No, because this requires 2 and you just have 1. Can you steal this? No, because it has 1 left. So the thief will steal this because the thief is not educated. So he will just have a value of 60. But if I go, I'm educated. So if I'm educated, what I'll do is I'll steal this guy, which will initially, if it is 6, it will still be left with 4, and I'll get a value of 40. Then I'll steal this and I'll get a value of 30, and the weight will still be, like the remaining weight will still be 1. You can still steal elements of weight 1, and I made a weight of 70 because I was educated and I applied dynamic programming. Why did greedy fail? Law of uniformity that I have explained. Uniformity was not there. Uniformity was not there because over here it's 60, then it is 40, then it is 30. There's nothing uniform. Over here for less weight, the value is more. Over here for more weight, the value is less. So there is no uniformity. You're not sure that if you pick the valuable items, the other elements might, as you see over here, if I pick these two, they ended up summing up more. So uniformity is not there. You don't know, in the future you might get someone who adds up to give better. So as long as uniformity is not there, you definitely cannot apply greedy. So you're educated. That's why you'll think of trying out, yes, you will think of trying out all combinations. Yes, you are educated, so you'll think of trying out all combinations, and among those combinations you will take the best value, best total value giving combination. Make sense? And how do you try out all combinations? There's only one way, and that's recursion. Yes, you try out recursion to have all the combinations, and whichever combination gives you the maximal, remember this, gives you the maximal value will be your answer. So in order to write recurrence, what are the rules? Follow the standard rules. Express everything in terms of index. The first element will be index. How does that make sense? Because again, we are given a, assume these are 3 items. So you can say 0th item, first item, second item. Express this as an array. So you can think in terms of indexes. This can be an index, this can be an index, this can be an index. First rule satisfied, expressed in terms of index. Because in the entire DP series I've been saying you express everything in terms of index. So that's what we do. What is the next thing that you will do? The next parameter. Guys, what is the next parameter? The thief has gone to steal with a bag. So he needs to be careful if the bag is full or not. So I can say bag weight. I can say bag weight is the next criteria where we see that if the weight is still there or not. So I can say the bag weight, I can say is capital W. So you'll express everything in terms of index as well as W. Okay. So that's what you will be doing. Fine. What's the next thing? Explore all possibilities. Now, what possibilities can he have if he's at what possibilities he can have? DP on subsequences is what we are learning. Pick and non-pick. Yes, the possibilities will be pick and non-pick. Already explained this in DP14. DP14 is the first one of DP on subsequences. So go and watch it. Pick and non-pick. Next, You're looking for the maximal. Yes, you're looking for maximal. So max of all possibilities is what you take. So if you can do this, you can easily solve the knapsack using the recursion. So what are you waiting for? Let's get started. So f of index and w. So assume the initial call to be made to f of n minus 1 and w, where you say that, hey, listen, for an example, let's take this example of 3, 2, 4, where we had 30, 40, and 60. So if this is the array, you're basically saying, if I write down the indexes, it's 0, 1, 2. You're basically saying f of 2 with a bag weight of 6. So what does this mean? Till the index 2, what is the maximum that you can generate till, let me write this, till index 2, what maximal value you will get with weight of bag as 6. That is the meaning. Till index 2 what is the max value you can get with the weight of bag to be 6. That's the meaning. Fine. So we have written this, and we can think of base cases afterwards. That's the state. So we have a more or less express them in terms of index and w. Next is explore all possibilities. Now tell me one thing. If you're standing at a particular guy, what options does the thief have? What options does it have? Again, very, very easy. He'll either steal it or he'll not steal it. So he will have two options. Either he will decide to not take it, or he'll decide to take it. Like, I don't think of any other options. Can you do something apart from this? Obviously not. Either you can pick up that element and put it into your bag, or else I'll not put that into my bag. Again, makes sense. So if I'm saying not take, then what happens? You'll move to the next item. You'll move to the next item. Make sense? And the value that you will add to yourself. Because what does f mean? F means max value. So the value that you will add will be 0 because you haven't added anything. And you'll move to the next index, which is index minus 1. Because if you are standing at this guy, you did not pick this. So you'll go to the next and you'll start seeing from here. And will the weight be same? Obviously, if you're not stealing anything, will the weight of the bag diminish? Obviously not. It will not diminish, right? So you'll move back. Perfect. Now, can you take is the question. So since you're trying out maximals, probably initially you can keep it as int mean, assuming you did not take it. So thereby the costing will be int mean. Why int mean? Question might arise. Whenever you compute maximal, try to initially assume it as int mean so that the take case is not considered. Why? Because assume your bag has a weight of 6 and there is an item with weight of 7, and let's say a value of 10,000, a huge value. Can you steal this? No. Why? Because the weight of the item is greater than the weight of the bag. So it's very important that when you are checking out for the take case, you always check. Yes, you always check. Am I allowed to steal it? Can my bag even take this? So I'll be like, okay, weight of this guy has to be lesser than equal to the weight of the bag that I still have. Like, if I'm having a bag with weight, it should be still lesser than this. And over there, you can say, okay, if it is, then I can steal. And if I steal, the value that I will add will be value of index. And if I'm stealing this current guy, I will move to the previous guy. I'll move to the previous guy. Make sense? And what will happen to the bag? Dude, you're stealing something. You're putting that into the bag. So the bag will reduce now. So what are you waiting for? Let's reduce the bag with W minus WT index. That is the value it will reduce. And what did the question say? Give me the maximal value. So there are two choices, either not take or either take. So whichever choice gave you the maximal, you will directly return it. So that's a very simple one, and we have been doing this not take and take in all the DP on subsequences. Just a slight change of pattern. You have to find the max. So whenever you're looking for values, add them, generate the values. Keep by adding, generate the values. Okay. So now the question arises: what are the base cases? So we have completed all the three steps of the recursion, which is express them in terms of index and W, explore all possibilities, and take the max of all possibilities, right? So what is the next step? Obviously, writing the base case, and we have started the recurrence from n minus 1. So we will write the base case at 0. Remember this always. If you're starting it from n minus 1, try to write it as 0. You're starting from 0, try to write it of n minus 1. So what I'll do is I'll write the first thing. If index equal to 0 is my base case of the recursion. Now we can think of it afterwards. Let's try. Right? Let's try to think. So what does this mean? F of 0 W. What does this mean? The thief has come, like the thief just has a single element and with a bag weight of W. What is the max value that he can get? What is the max value that he can get? If the thief is just at here and he has a W weight, assume the weight is 6 of this guy and it's giving me a value of 10,000. The thief is coming with f of 0 and the W as 8. And this is the last element. What will the thief do? What will the thief do? Yeah, dude, it's the last element at the home, in the home. Will he steal it? And why will he not steal it? He still has a bag weight of 8 left and it will just take 6. As long as he can fit this in, he will steal and go. So do that. He'll be like, okay, if the last element can fit in my bag, I will take this. And if I take this, what is function giving? The max value. So it's a single element. There's only one value that you will get, which is value of 0. Makes sense. But if the thief comes up with something like a bag weight of 4, can he steal? No, he cannot. Why he cannot? He has come to the last item, but the weight that he carries is 4. And despite this guy giving him a lot value, 10,000, it will take a place of 6. And he just has 4. So he cannot. So if he cannot, can you get some value? No. So what you can say is, if it is less, I'll steal it. Or else I'll return a 0 saying, I cannot steal it. There is absolutely no way that I can steal it. That's how you can easily think of a single element. Try to think the base case in terms of a single element always. So that's how the entire recursion can be easily written. So if I talk about the time complexity of recursion, what will be it? Again, you are trying out a couple of ways. So the time complexity will be 2 to the power n. And the space complexity will be big O of n, because there's a lot of recursion stack space that you're using. So we saw that the recursion time complexity is 2 to the power n and the space required is big O of n. We definitely need to optimize this, and it's very simple memorization. But before that, let's understand how is this entire code working by taking the example that we did take to see where the greedy was failing. So let's take the weight as a 3, 2 and 5, and let's take the values as 30, 40 and 60. Okay, let's take the bag weight as capital W, that is as 6. So initially we start at f of, this is the index 0, 1, 2. So we start at index 2 and we have a bag weight of 6. What options do you have? You have 2 options, whether to not take it, whether to take it, right? So if we decide that we're not going to take it, can I say I will still be we'll go to the previous index, but we'll still be having the same weight? Okay, makes sense. But if I decide to take it, this element will be a part of my bag. So thereby this will give me a weight like the value of 60, but it says it is taking a weight of 5 from the baggage out. So can I say I'll move to the back index with 6 as the initial weight, but since you have taken a 5, you'll be remaining out with 1. Make sense? Absolutely. Now you are at f of 1, 6. What options do you have? Of not taking, of taking. So imagine at index 1, you decide you will not take it. So where will you move? You'll move to the 0th index and the bag weight still stays as 6. And if you decide to take it rather, what will happen? You'll move to the previous index, and if you take it, there will be a plus 40, there will be a plus 40, and then there will be a weightage loss of 2. Then there will be a weightage loss of 2. So there is a 6. So 6 minus 2 will be 4, correct? So we have two options, not pick, pick. So at f of 1 6, how will f of 1 6 look? F of 1 6 will be something like this. There will be something like not take, which will be 0 plus f of 0 6, and take will be 40 plus f of 0 comma 4. So tell me one thing, if you are at f of 0 6, yes, if you are at f of 0 6 and you have a weight still 6 of the bag, will you try to steal it? Obviously. So thereby this returns value 30. And if you're at here and the bag weight is 4, you can again steal this because this is a 3 weight. So I'll decide to steal this and there will be a 30. So 06 returns 30, 04 also returns 30. Thereby not take becomes 30 and take becomes 40 plus 30, 70. Which one will you prefer? Take. So thereby this guy gets 70. So that's what f of 1 6 will return, 70. Perfect. So I'll just erase the bottom tree. So f of 1 6 got 70. Now let's come back to this f of 1 1. If I decide I'll not take it, what will happen? If I'm not taking it, I'll move to the previous index. And I will still have the same weight. Agreed? What will happen at f of 1 1? Again, you'll decide to not pick it and you'll decide to pick it. But can you pick it is my question. You are at the first index and it requires a weightage of 2. But you're having a weightage of 1. So you definitely cannot pick it. So thereby, if you remember the recurrence, it will stay as int mean, right? So this will be int mean because you take is not possible. And if you decide to not take it, you'll move to 0th index with a bag weight of 1. Now tell me one thing. This is demanding a weight of 3, but a bag weight is 1. Can you? You cannot. So this will return a 0. So let's analyze of 1 comma 1. So at 1 comma 1, not take says 0 plus f of 0 1. This gives you 0. And the take is int mean because that's not possible to take. So 0 is maximum or int mean is maximum. Definitely 0. So f of 1 of 0 will return 0. This guy will return 0. So let's quickly erase this. Let's write the next step. What's the next step? F of 2 6. So you're at f of 2 6, correct? What are the options? You decide to not take. So if you decide to not take, you get 0 plus f of 1 6, which is 70. And if you decide to take, that's 60 plus f of 1 1, and this is 0. So 70 is more or 60 is more? Definitely 70. So this returns 70. And that's very obvious because if you pick up these couple of guys, it gives you 70. So actually we're trying out all ways and we eventually got 70, right? So what is the next step? Obviously the next step is memoization, right? And what are the indexes? Like what are the changing parameters? Index and W. So according to the rule, very simple. What's the maximum? N. What is the maximum? W. So we create this plus this size array because index will be from 0 to n minus 1. Weight can be from 0 to W. So thereby we create n and W plus 1 array. So this is the DP array that we will create, right? So over here we can write DP of index of W equal to this. And over here we can just insert a line of DP of index and W not equal to minus 1. Then return the value. So the memoization has been done. And what will be the time complexity, guys? Big O of n cross W. What will be the space complexity? Big O of n cross W. But there will be a stack space of big O of 1 due to the recursion that goes deep. So there will be a auxiliary stack space. But do I like that? Obviously not. So I need to remove it. And how do you remove it? We convert this into a tabulation code. And what is the rule of tabulation? Base case is what you first write. Then write the changing parameters, index and W. Write both the changing parameters in nested loop. If there are 3, it will be 3 nested. If there are 4 changing parameters, 4 nested. 5 changing parameters, 5 nested. Depending on the number of changing parameters, you write them. And what is the last thing? Copy the recurrence that you have been doing. Why? Because what is memoization? what is rather recursion plus memoization? It's top down and then accumulate and get the answer. Top down. What's tabulation? Bottom up, bottom up, bottom up to get your answer. Bottom up. So I can say, what is the base case? Firstly, INTDP of NW to be declared, right? What's the base case? Let's quickly check out the base case. So time to think about the base case. Now we know this is N, this is W, and this is the weight that the thief has on his back. Can I say, if I analyze, for what states will the value be 0? Whenever index is 0, so I can say for anything like 0, but the state W has to be greater than WT0. Assume WT0 to be 5. Assume the weight to be 5. Then if I bring in 4, like this one is 4, then it will return you a 0. If I bring in 2, it will return you a 0. If I bring in 1, it will return you a 0. But if I bring in the weight to be 6, that's possible. If I bring in to be 5, then this guy will be executed. So can I say, for everything, for every weight greater than 5, I can steal it? Make sense? So I'll be like, okay, for every weight from 0 till W, I can steal it. And if I steal it, the value that I'll get is 0. And apart from this, everyone will have 0. So probably I can keep it as 0. Everyone will have 0. Only for the weights that are greater than this guy or beyond this can steal it. So thereby value 0. Done. First job done. What's the next step? Look out at the changing parameters of your recursion. Index, WT. How are you moving them? How are you moving them? Just have a clear cut vision of it. So you're like, okay, Striver, we are moving the index from n minus 1 to 0 in the recursion. But this is bottom up. So you'll move it opposite. The 0th case is done over here. So you'll move it from 1 to n minus 1. What about the weight? Again, you're moving the weight from W till 0. So you'll do it opposite. It will be 0 to W. It will be 0 to W. Okay, and then copy the recurrence. So that's the funda that you have to apply. Just write 2 nested loops and copy the recurrence. You will be pretty much done with the tabulation. And after that, I'll teach you space optimization. But yes, don't skip the video now, because at the end, I'll teach you how do you convert a 2-row. Like we have learned 2-row space optimization, right? We have learned 2-row space optimization. But over here, we will learn 1-row space optimization. Okay. So without wasting any time, let's quickly code this up. So I've been given a weight, a value, a n, a max weight. Okay, so can I write a function int func int index int bigger w, a vector of int or weight value. I think int. There will be no requirement of n. Yeah, I think that makes sense. I know if index is 0 and if the weight of 0 is lesser than w, I can definitely steal it. So value, probably let's call it as wt. Let's call it as val, so that we don't have to write a lot. Val of 0. Else it will be returning a 0. Perfect. Now, can I say there will be 2 cases? Int not take. Perfect. And if I don't take it, it will be 0 plus f of, I'll move to the next index and I'll have the same weight and I can just carry the weight and val. And if I take it, probably I can say initially it will be int mean. And can I say if the wt of index is indeed lesser than the w, I can definitely steal it. And if I steal it, it will be value of index plus f of index minus 1 w minus weight of index comma wt comma val. And at the end of the day, I will return the max of take not take, right? And over here, I can say return f of 0, sorry, rather n minus 1 max weight, the weight array and the value array. And I think that should be pretty much it for the knapsack. And I think if I run this, should be giving me correct answer. Let's see. Okay, it is giving time limit exceeded. Again, very obvious. So what I'll do is I'll just take vector of vector int and probably I can take a dp and I can have it as n. Then I can take a vector of int. Remember this guy will be max weight plus 1 and comma minus 1, and just make sure you pass on the dp as well over here. And yeah, just carry it over here as well. Vector of int, again reference, very important, always take it via reference. dp over here, dp over here, and right before returning dp of index, and this will be w equal to, and right over here there will be a case where you check if the state has been previously visited or not. So dp of index and w is what you return. So if you just run this, should be super fine. See that the recursion is working fine. Now it's time to convert this into tabulation. First thing is this, and for every w which is greater than this, so the base case is very simple. For every w which is, you can say, greater than wt0, okay, let's make it wt in val, which is from here to, I can say dp of 0 and w will be value of 0. Again, makes sense. And right after this, I can say there will be a couple of loops. One is the index, starts from 1, goes until 1, and index plus plus. For int w equal to 1, or rather 0, w lesser than max weight, which is the max weight, and w plus plus. And what you write is these, just copy paste the records. As simple. So see how easy the tabulation is. Like, I don't think it's that tough now to you guys if you're following the DP series. So I will just erase this, and you'll see that, okay, let's quickly write this as well. dp of wt index, w minus wt, right? And over here I can just quickly erase this as well, and this will be dp of index w. Does that make sense? Yeah. And over here, return of dp of n minus 1 max of weight. So that will be it over here. And and you see everything is passing. Let's quickly submit this. So we have pretty much done it. And now you know how to space optimize this into, because whenever there is an index minus 1, you know what to do. Instead of this, you end up declaring just couple of rows. So let's declare a couple of rows. Again, I have been doing this throughout, that if there is index minus 1, you space optimize. If you're not following the DP series, then it's your problem. You're missing out on a lot of things. Please make sure you follow the DP series. So I can say I'll take a previous of max weight plus 1, because what we are using is, we're just using the previous rows, right? Because the DP is computed like this guy. Like if I just write it, how's the DP computed? First you filled up these guys, right? With help of this. Then these loops will fill this, then this, then this, and so on. So whenever you're filling a particular row, what are you using? Using the previous index minus 1 means this row. So you're just using the previous. We don't need this any further. Whenever you are filling this guy, we just require this guy. There is no requirement of this. So I'll just keep on using this concept, and we can easily do it. So how do you do it? Previous this comma 0 and cur of max of weight plus 1 comma 0, right? And I can just simply omit this. And once I've omitted this, what's the next thing? Instead of dp of 0, can you please write previous? We can. And over here, instead of this, we'll write current. Instead of index minus 1, we'll write previous. Amazing. Instead of dp of index minus 1, we will again write previous. Make sense? And over here, what I can say is, I'll return previous of max weight, and over here curve will become, rather previous will become curve. And this is how you can space optimize this into only couple of rows. Like I've just done couple of rows, and you'll see it's definitely running fine. But can we optimize this? Because over here also we're using couple of rows. Can we optimize this? Yes, we still can optimize this. If we apply some of the brains, we definitely can optimize this. Let's actually look at the records. What are you using actually? You're saying, okay, w minus wt. Okay, makes sense. W minus wt is what I am using, right? So can I say, let's try to write this on iPad and try to understand. So whenever you are trying to compute this index. Assume this is the index. W starts from 0, goes on till max weight. First, you try to compute this. In this case, what are you using? You are saying the previous row, index minus 1, which is the previous rows, whatever W minus whatever, some value. So imagine your W is standing here. Yes, imagine your W is standing here. Then W minus WT of index, where will this guy be? It cannot be in this half. Can it be in this half? Definitely not. It will be somewhere here, somewhere over here onto the left. Okay, makes sense because W minus WT index will be somewhere here. Correct? Now you'll be like, but Striver, tell us one thing. How does this help? Because we are first filling this guy, then this guy, then this guy, then this guy, then this guy. Who has said you to do this? Who has said you to do this? Can't you do it opposite? Like if I ask you, if we do it in this way, is it wrong? If I start W from here and then I go filling this, 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 can I actually do this? Is it possible? Yeah, it will still give the correct answer. Why? Because when we are filling this, it is never dependent on these values. It is actually dependent on the previous row. It is actually dependent on the previous row. So in the code, even if I write the opposite, where I say I will just do it like this, WT, and weight can be greater than equal to 0, and W minus minus, and if I try to run this, you will see this is also fine because we are not dependent on the previous guys. We are dependent on just the upper row. We're just dependent. So you see it is running fine because we're not dependent on these guys. This guy is computed with the help of the previous row. So what if I just change it? So that's the first change I do. Now tell me one thing. If this is the previous and this is the current, right? And initially this current is having nothing. So I'll come over here and I'll try to fill it. So when I try to fill it, I will definitely use some value from here, probably from here, or probably from here, or probably from here, due to this concept. So instead of filling it here, instead of using the current, can I not fill it here? For this guy, can I not fill it here? I can. For this guy, can I not fill on the previous itself? I can. For this guy, can I not fill on the previous itself? I can. For this guy, can I not on the previous? I can. For this guy, can I not fill here? Yes. Why does this work? Because this guy means there is no need of the right elements. If I'm starting to fill here, if I fill till here, we will never require these elements of the previous row any further. Whenever we are here, this portion will never be required. This portion will be filled with the left guy. So you'll use the same previous row. To fill it up. Make sense? Thereby, what I said was, I'll use the same previous instead of using the current row any further. I'll use the same previous again and again. Why? Let's repeat this. What did I say? If I'm trying to fill this, then I'm just requiring the left guys. So if I try to fill it from the right, if I'm filling this, then I'll require these guys. So these guys are intact. Fill this up. Then when I fill this, I'll just require these guys. Fill this up. When I try to fill this, I'll just require these guys. Fill this up. When I require this guy, I'll just require these guys. Fill this up. When I require this guy, I'll require this guy. Fill this up. When I require this guy, there will be no one. So apparently, eventually, there was a previous with some values. When the next row calculation came, you stored it over here, then here, then here, then here, then here, then here. So automatically the previous is acting as the current row every time because you're filling from right to left. Why can't you fill from left to right? Very obvious reason. Because if it is storing some values, if you start filling here, then if you start filling here, this guy will require the previous guys, but you have overridden the previous guys. So when you try to compute this, you'll use the current values which are not correct. So thereby, left to right cannot work. Only right to left will work. Only right to left. Thereby, I can say, let's go back to the code. I don't need the current. Yes, I don't need the current. Instead of that, I just require the previous. And over here, I can say previous. And there is no need of this. So, assuming I've omitted everything, now let's run this and see if this is running fine. We see some error which is saying W is not declared in the scope. Why is it not declared in the scope? Okay, sorry. Over here. Fine. Let's try to run this off. Amazing. One row and it does. Submit this. Single array space optimization, not even two rows. And I bet you did love this. So just in case you did, please hit that like button in the comment section. Let me know how was this. Like, did you love the one array optimization technique? If you did, please do write. Please do write. Like, I'll really appreciate that. Also, if you're new to this channel, please do consider subscribing to us. And yeah, with this, let's wrap up this video and meet in the next one. Till then, bye bye, take care.